In this video, we're going to try and come up with parametric equations to describe the path of this cycloid. So suppose you have a circle of radius a, and if you were to roll this circle in this direction and keep track of this point here will trace out this path. Well, this path here is called a cycloid. Just on a side note, if you were to turn this cycloid upside down, it would look something like this. Okay, and let's say this cycloid is frictionless. So if you were to put let's say a marble here, the time it takes to do this, let's call it t1, would be the same as the time it takes to do one scoop here. So let's call this t2. For cycloid, t1 will equal t2. No matter where you put the marble, the time it takes to do one scoop will always be the same. But that's not true if you have a circle. Let's say you've got a perfect circle. If you put a marble here, this time here will be different from this time here. So the interesting thing about the cycloid is that no matter where you put the marble, the time it takes to do one scoop will always be the same. If you look at a pendulum, the pendulum is really following a circle because of radius, the length of the string. A pendulum, in the past I would give you time equals 2 pi root L over G. Well, this is not precisely true because this thing here is following a circle, but the time for a cycloid will always be true. This is true for around this, well, it's a good approximation for around this region, but if you put it too far up here, the pendulum doesn't really follow this equation. Well, anyway, that's another side story. Let's go back to this. We are trying to work out the equations to describe this path. So hang on. So when you roll this circle, it will take you to this. Hang on. It will take you to this. So we're going to set up our parametric equations. So we could set up the time. You could say, oh, let's one cycle be from 0 to 1. Let's say 1 second is one cycle. You could set up t to be like this, but then that would be really complicated because suppose t is somewhere around here. Suppose t is somewhere around here. How would you keep track of the height of this thing? Remember, with parametric equations, we are interested in the x direction, and we are interested in the y direction as we vary time. But if you set up one cycle as being 0 to 1, then suppose t is somewhere around here. It is very hard to keep track of this distance here, this height, and it's also very hard to keep track of this width. You see, if you have an angle to work with, then you can combine the angle with sine and cos, and then you can keep track of the height and the width. You see, if you set up your time so that one cycle is from 0 to 1, then it's very hard to keep track of the height. But if you set up your time in such a way that one cycle is from 0 to 2 pi, then you see, if you can set up your time to coincide with the angle, then you can use the time to represent the angle. So if you can use if the time ties in with the angle, then you can sine the time, which will mean you're really signing the angle. So setting up your one period as 0 to 1 is not a good idea. It is better to set up one cycle as 2 pi, from 0 to 2 pi. Then one increment of time will equal one increment of the angle. Another increment of time, then there will be another increment of the angle. So this t will tie in with the angle. So that will help you keep track of the x and y. So we need to keep track of this x, and we need to keep track of this y. Let me think. So this angle, this distance here is actually a t, because I will continue in the next video. Okay. Yeah, I will continue in the next video.